Well, hello everybody. Welcome to another wonderful day of class. If you recall back to last Thursday, what we were talking about was we did proofs by contradiction. And so what we've worked on so far is different proving techniques. We talked about direct proof and contrapositive proof and proof by contradiction. So today what we're going to do is we're going to expand upon that and find new proving techniques. And what we're going to look at are actually different types of theorems that aren't always if-then statements. So the ones we've done so far have been a lot of if-then statements. Here we're going to have things that may not be of that form. So the first thing that is very close to an if-then statement, but not quite, that I do want to talk about is an if and only if statement. So here we have a theorem, the integer n is odd if and only if n squared is odd. So the distinction here between an if-then and if and only if is that an if and only if goes both directions. So what that means is that we actually have to break this up into two theorems, is we first show that if an integer is odd, then n squared is odd. And then we can show if n squared is odd, then n is odd. So just to point out what an if and only if proof would look like would be, well, instead of just showing one proof, you actually have to do two. You would have the new theorem, if n is odd, then n squared is odd. And then you'd have to prove if n squared is odd, then n is odd. Now within this context, if you focus on just this one, you could use a direct proof here to say that if n is odd, then n is congruent to 1 mod 2, so n squared is congruent to 1 times 1 is 1 mod 2, therefore n squared is odd. This one would probably be better to do a proof by contrapositive, so that is, I would assume n is not odd, so n is even, and I'd have to show n squared is even. But if n is even, n is congruent to 0 mod 2. 0 times 0 is 0 mod 2, so n squared is congruent to 0 mod 2. I'm not writing all of that up at the board because we've actually done those both in class at some point before. Now the difference here is that I'm just trying to show you that because it's an if and only if, we first prove this statement and then we prove this statement. So it turns, instead of having one proof, we do two. And that's the only new thing that we have with if and only ifs. All right. Good job. So as I look at the next one, the next type of theorem that we're going to look at is, let n be an integer, then the following are equivalent. We have n is even, n is congruent to 0 mod 2, and n squared is congruent to 0 mod 2, and n squared is even. So the difference here is that we have 4 equivalent statements. So with these 4 equivalent statements, what we get is, okay, well what we're really saying is that one if and only if 2. So we'd have to do 2 proofs there. We'd have to show 1 implies 2 and 2 implies 1. We also get 1 if and only if 3. So we'd have to do 1 implies 3 and 3 implies 1. And then 1 if and only if 4. So 1 implies 4 and 4 implies 1. Then we also get 2 if and only if 3. So we have to do if 2 then 3, and then if 3 then 2. And then we'd have to do 2 if and only if 4, and 3 if and only if 4. So what we end up with is, if we try to use the same technique we just did, we're going to end up having to do 12 distinct proofs. So we'll have to do 12 if-then proofs in order to get that these are all equivalent. That sounds like a lot of work. So instead what we're going to do is we're going to think about this in a slightly different way. And we want to set this up just so it's a little less work. And so if I want to show 1 and 2, 3, and 4 are all the same thing, what I'm going to end up doing is, well, I'm going to show some type of circular argument here, and I'm going to show that, for example, I'll start with 1, and I'll show that 1 implies 2. So if 1, then 2, and if 2, then 3, and if 3, then 4, and if 4, then 1. And so that's what I mean by it's circular, is I go 1 to 2 to 3 to 4, all the way back to 1. Now if I do that, notice that I have 1, 2, 3, 4 proofs to do instead of 12, so I've saved myself some time. But the idea is that by showing this, I also have shown that 2 implies 1 by showing, well, 2 implies 1 because 2 implies 3 implies 4 implies 1, therefore 2 implies 1. I also get 3 implies 1 by the same reasoning, and 4 implies 2 because 4 implies 1 implies 2. And so because we have this circular path here, we get that, well, all of them imply each other. Therefore, each of them is true if and only if the others is true. So they are all equivalent statements. Now, I do want to point out that you don't necessarily have to go in this order, 1, 2, 3, 4. You could go 2, 3, 4, 1, or you could go 2 implies 4, implies 1, implies 3, implies 2. But the important thing is that you do get a loop that goes through all of the numbers. So if you did something like 4 implies 3 implies 2, notice that there's no 1 in there. Or if I do a 1 implies 3, well then I don't get the circle because I can't go from 4 to 1 because I can't go backwards with the implications. So I'd go 4 implies 3, but 1 implies 3, but these aren't necessarily the same. So what I need is a picture like this where all of the things that are equivalent fall within this loop of proofs. So I just run through each of those proofs in order. All right. With that, what we would do is say, if I look at this one, 1 implies 2, what I'm trying to show is that if n is even, so I get to assume n is even, then n is congruent to 0 mod 2. Now, I tried to make these first ones fairly easy because we've actually done this. We know that n is even is equivalent to saying n is congruent to 0 mod 2. So if n is even, it's divisible by 2. Therefore, when I divide by 2, I get a remainder of 0. Therefore, n is even is equivalent to saying n is congruent to 0 mod 2. Here, because we've done this, I don't even need to necessarily write out anymore. I'm just checking, yes, that is true. The next thing we had was assume n is congruent to 0 mod 2, and I want to show that then n squared is congruent to 0 mod 2. Now that does take a little bit more work. So what we would say is something like n squared is congruent to n times n, so this is 0 squared mod 2. But 0 squared is 0 mod 2. Hence, n squared is congruent to 0 mod 2, which is what we're looking for. Then we would say, assume n squared is congruent to 0 mod 2, then n squared is even. And again, this is one that follows by definition that it is congruent to 0 mod 2 if it is even. So replacing n with n squared, we have the same proof. We don't necessarily need to do that one again. So these are equivalent statements. The last one is I have to show 4 implies 1. So I'm trying to show if n squared is odd, then if n squared is even, then n is even. So now this one, as opposed to doing directly, we could do a contrapositive proof because it's going to work out a little bit easier. So what I would do is assume n is odd, then n squared is odd. And actually, as opposed to going through this proof again, we just talked about this one in the previous slide, which is why I did this one in the previous slide. So if n is odd, we knew that n is odd if and only if n squared is odd. So if n is odd, then n squared is odd is true. So we get 4 implies 1. So what have we shown? We've shown 1 implies 2 implies 3 implies 4 implies 1. Hence, if we just follow around in a circle, we get that all 4 of those things are indeed equivalent. Any questions on that one? All right. So we have that these things are all equivalent, and we could end up showing any number of things are equivalent. Instead of showing 4 things, we do 5 or 6 or 7. And the point is that it just ends up being less work if we try to work in a circle instead of trying to show both directions each time. Now, I do want to point out that the previous 2 examples weren't all that different than what we've been doing. They were just if-then statements or conditional statements. They just were a little bit more involved because we go both directions, or we have to show how things imply each other. And so I just wanted to make sure we outline how to do those proofs, whereas what we have now is a new type of theorem, and is there exists a unique even prime number. So what we're pointing out here is that we're not saying if this, then that. We're just making a claim there exists a unique even prime number. So what we're going to have here is what's called both an existence proof and a uniqueness proof. So we have to show that there exists an even prime number, and we have to show it's unique. So for existence, the idea is just you have to find one. So maybe you guys can help me out here. Can you think of a number which is both even and prime? So I see 4 and I see 2. Very good. So those are both even. However, notice that 4 is not prime because 2 times 2 is 4. So 4 is divisible by something other than itself. However, 2 is prime because the only divisors of 2 are 2 and 1. Therefore, it's only divisible by 1 in itself. Therefore, 2 is both even and prime. So it's even because it's divisible by 2, which is itself. So to show you existence, you just say, note that 2 is an even number and a prime number, therefore such a number exists. To show uniqueness now, we have to show that the only even prime number is 2. So how would we do that? Well, let's think about that. In general, to show uniqueness, what we have to do is assume that A and B satisfy whatever property we're interested in. So in this case, suppose that A and B are even prime numbers. What I have to do is to show uniqueness is I have to show that then A is equal to B. So that is, if I thought I had 2, they were actually the same thing. So if I have anything else, well, it has to be the same thing. So therefore, there can be only one answer. And so that's how we're going to show uniqueness, is we would assume that we thought we had 2, but they're actually the same thing. Now, in this case, because we already found one, instead of using an arbitrary A and B, I can say A and 2. So I already know 2 is one of those, so suppose I had some other one, then what I want to show is that A is equal to 2. The original setup was a more generalized case, is that we can just say, in general, if we had an A and B, then A is equal to B. But we're going to say, let's suppose that A is an even prime and 2 is an even prime. I want to show that A has to be equal to 2. All right. Well, note that A is even. So what does that mean? Is that 2 divides A. So if I just start working through, I'm just going to write down things that I know. Since A is even, 2 divides A. However, also, A is prime. So that means that only 1 divides A and 2 divides A. I'm sorry, A divides A. So the only divisors of A are 1 and itself. Notice, however, that 2 is not equal to 1. And since the only divisors are 1 in itself, what does that mean? Well, we found a divisor which was not equal to 1. Hence, A has to be equal to 2. So, A has to be equal to 2. So if we have any other even prime, well, because it's even, it's divisible by 2, but because it's prime, it's only divisible by 1 in itself. Therefore, the number has to be equal to 2. So 2 is indeed the only even prime. Does that make sense? All right. Pinoy, I see you're having troubles with Discord. If you are having troubles getting in and the link doesn't work, you can somebody else help him out. But if you've signed in before, yes, you just have to re-sign in. You don't need to go through the link again. You just need to sign into your Discord account. And you should already be in the chat room so that you can join us there. Again, I'm going to avoid putting it on the comments just because the first day we tried this, we had a bunch of people in there doing weird things. All right. After class, though, I will check the link and redo it just to make sure it's still working. Going back to what we were talking about is we've now done an existence and uniqueness proof. And so we're going to do another existence and uniqueness proof, but this one will be a little bit more interesting. So, and we're going to need this one for another proof later on, and we're actually going to use this quite frequently, is that what we're going to have is suppose that A is a non-empty finite set of real numbers, then what I claim is that A has a unique smallest element. I further claim that it has a unique largest element that we'll get from a similar proof, but we'll talk about that as we go. Alright, so as I go up to the board for this one, the first thing I want to point out is what is the smallest element of A. So to give a definition, that I haven't defined this before, so I need to be precise. The smallest element of A, I'm going to say little a is the smallest element of A, or the minimum of A. Generally, minimum would probably be a more common usage in mathematics, but I'm just going to say smallest. It's a little more colloquial. If we have that both A is an element of A, and if B is in A, then A is less than or equal to B. So what we want to show is that, or what we're saying is that a smallest element is an element that's actually in the set. And furthermore, it's less than or equal to every element in the set, which would include itself, because A is less than or equal to A, so A has to be less than or equal to every element in the set. All right. Now, the goal is to show that for a finite non-empty set, that there has to exist the unique smallest element. I'm actually going to show uniqueness first. And so for uniqueness, I don't actually even need existence, because uniqueness means there's at most one, whereas existence means there's at least one. So I can show that if there were two, they would have to be the same, without even knowing if there even is one. So in general, if I start with any set, I don't know necessarily that it has a smallest element, but if it does have a smallest element, then it will have to be unique. And so if we think back to perhaps your calculus days, you talked about the global minimum. The global minimum of a function doesn't necessarily exist, but if it does exist, it is unique. And that's similar to what we're showing here. All right, so what we can do is let A and B be smallest elements of A. So suppose I have the two elements A and B, and they're both the smallest elements. what I want to do is then A is equal to B. And how are we going to do that is notice that, well, A is the smallest element of A, and B is the smallest element of A, so B is an element of A. Therefore, what we get is A is less than or equal to B, since B is in A. That is, B is an element of A is the smallest one, so A has to be less than or equal to B. By the same reasoning, B is less than or equal to A since A is an element of A. So this is an element of A, this is the smallest one, so this has to be less than or equal to it. So what we end up with is that A is less than or equal to B is less than or equal to A. Notice that the only way that can happen is if they're equal. That is, if B were bigger than A, that would mean that this is not true. If B were smaller than A, it would mean that this is not true. So the only way we can have A less than or equal to B less than or equal to A is if A is equal to B. And this is an idea that's going to come up again. If we can show this, then that implies that A is equal to B. So if we had two smallest elements, they'd actually have to be the same. So if there is a smallest element, it has to be unique. And so we've actually done uniqueness first. All right. Now, existence. So I have a finite non-empty set A, and I want to show that the smallest element exists. Well, if we use what we did last time, that means that we have to find any smallest element. So I have to determine what it is and then tell you and show you that it is indeed the smallest element. So like the last one we said 2. It is even and it is prime, so we have existence. However, in this case, A is just some arbitrary set. So trying to figure out what the smallest element is isn't the easiest thing in the world. I don't know what it's going to be. I don't know what elements are in A. So I'd have to do something in a general way to say, okay, well, let's take the elements and let's do some type of sorting thing so that I can eventually get out the smallest element. And I'll have to make sure that whatever I do will work for any non-empty set. I actually have that posted on the website if you're interested in seeing what that looks like. But what I'm going to do instead is I'm going to notice, okay, if it's hard to show you existence, what I'm going to do instead is I'm going to do a proof by contradiction. So it was hard to directly show that the square root of 2 was irrational, so we used a proof by contradiction and assumed it was rational, and it made things easier. So what we're going to do is assume that A has no smallest element. And what we want is to get a contradiction. Therefore, this will have to be false. So if it has no smallest element is false, then it has to have a smallest element. Are you guys following that so far? Does that make sense? All right. Well, all right. What I want to say now is say, okay, well, what do we do? How do we proceed? Is note A is non-empty. So I do know that there exists some element in A, and so I'm going to call it A0. I don't know what it is, but there is some element in A. This would not work if A was empty, and if A was empty, the empty set doesn't have a smallest element, so that does fall apart, but because we're assuming it's a non-empty set, there has to be something in A, so I'm just going to say there's something in A. Now you guys can help me out here. If there is no smallest element, can A0 be the smallest element? It seems like my wife is drawing a bath for one of the kids, so if that is coming through the mic, I apologize. Alright, so I did hear no, it cannot be the smallest element. So what does that mean? Is there has to be something smaller. So since A0 is not the smallest, there exists an A1 in A with A1 less than A0. All right, can A1 be the smallest element? Well, no. So there has to be, and so I won't write this all over again, but there has to be an A2, which is less than A1, which is less than A0. Notice they can't be equal because it has to be strictly less than, because this can't be the smallest. There has to be something strictly smaller, something strictly smaller. But A2 can't be the smallest, so there has to be an A3. Hopefully you guys see where I'm going with this. If there has to be an A3, there has to be an A4, 5, 6, 7. I have to keep going. How long do I have to keep going if there's going to be no smallest element? Well, I'd have to go forever, wouldn't I? Yeah, so, exactly. Thank you. I'd have to go on forever. So if I have to go on forever, each of these elements is in A. I'm going on forever. That means how many elements are A in A? That means that there are infinitely many elements in A. So, I go on forever, so therefore there are going to be infinitely many elements in A. So I found infinitely many elements. Well, that can't be the case. Why not? Because we decided A was finite, or that's what we assumed, right? So what we get is that A is both infinite and finite. Hence, we have a contradiction, because it can't be both infinite and finite. Therefore, a non-empty finite set has to have a smallest element. So this statement is false, because we found a contradiction. So what we get is that a non-empty finite set A has to have a smallest element. Does that make sense to everybody? All right. I just want to point out you can show it has to have a greatest element as well, because the only thing that would be different is you would say A0 is less than A1 is less than A2. So if we have a finite non-empty set, we have to have both the smallest element and a largest element, or we have to have a maximum and a minimum in that set. All right. Now, I really like this proof because it's one of those ones that keeps coming up later on as we continue to do more proofs. If we want to prove something happens, a lot of times we'll show we have a finite non-empty set, so it has to have a largest and smallest element, and that will give us something that we can use. In what way? It depends on the situation, but as we continue the next proof, we are going to use that again to get out something more interesting even, and so we will be using this one as we continue in the class, and it shows you, oh, well, if we want to show that something has to exist, not only can we do that by finding the element, we can do that by proof by contradiction by assuming it doesn't exist, and then getting something like, well, a finite set would have to be infinite. All right. This next theorem is also a major one that we're going to use a lot. And actually, I am using this quite frequently in my abstract algebra course that I'm also teaching. And it comes up quite a bit because there's a lot of number theory stuff that goes along with it. And it is a very useful, interesting theorem. However, as such, I do want to point out that this proof is going to be complicated because that's the way it normally works, is a lot of the more interesting, useful things end up just taking a little bit more work. So forewarning, before we do this proof, if you're going to get lost along the way, that is okay. Most people do. What I'm going to try to do is to break this up into really small pieces so that you can focus on one piece at a time. And every once in a while, I'm going to remind you why we're doing that and how it fits into the bigger picture. So the reason why I'm doing this proof is not only because it's interesting, but because along the way, the little pieces we do will highlight different proof techniques that you can use on the homework or on test. And so they're going to give very good examples of different things we can do with proofs. You know, with not only direct proofs and contrapositives and contradictions, but also showing existence and uniqueness, and showing using that finite non-empty set has to have a smallest and greatest element. So we're going to combine a lot of those things into one more interesting proof. With that said, if you do have questions along the way, please stop me and ask so that I can address those. But the first thing we need to show is that what is the greatest common divisor? So much like before I had a theorem where I hadn't defined the smallest element, I have not defined the greatest common divisor yet for you. And not only do I have to define it, I also have to show that my definition makes sense. That is, that there is going to be a greatest common divisor. So the greatest common divisor is, let's suppose we have natural numbers a and b. I'm going to say that there exists a d such that if d divides a and d divides b. So that means that d is a common divisor of a and b. d divides a and d divides b. Furthermore, if c divides a and c divides b, that is, c is also a common divisor, then c is going to be less than or equal to d. So there will not only exist, but there will exist a unique number d, where it is a common divisor in a and d, and all other common divisors are less than or equal to it. This will be our greatest common divisor. So my first lemma here is that such a number exists and is unique. All right. So how am I going to show such a number exists and is unique? Well, what I'm going to do is show that if I find the set of common divisors, it's going to form a set. And what I want is d is going to be the greatest common divisor. So if I can show that the set of common divisors has a unique greatest element, then I'll be done. So if I want to show that the set of common divisors have a unique greatest element, well, what I can do is I can show that the set of common divisors is a finite non-empty set, because if it's a finite non-empty set, we've just shown that it has to have a greatest element. So what we're going to do here to prove that the greatest common divisor exists and is unique is I'm just going to show the set of all common divisors is a finite non-empty set. So that's how these tie together. All right, so let's go ahead and do that. So let's let capital C be the set of all common divisors of A and B. And so that is the set of all, and since we're working with natural numbers, a set of all x and n such that x divides A and x divides B. All right. Now, in order to show this is non-empty, what I have to do is I actually have an existence proof, so I have to show that something exists in here. Now this one's not too bad. I can actually do that by finding an example. So if A and B are both natural numbers, can you guys think of a number which divides both A and B? I'll give you a second to think about that one. Very good. 1 divides both of them. So 1 divides A and 1 divides B. So 1 is an element of C. So C is non-empty. So I showed that there exists something in there because 1 divides both A and B, because 1 divides all natural numbers. So therefore, the set of all common divisors is non-empty. Now I want to show it's finite. So what I have to show is that there's an upper bound on how many elements can be in there. Well, what I'm going to do here is that suppose x divides a. I'm just trying to think here, and I'm not sure exactly where I'm going with this, but if x divides a, then a is equal to k times x for k an integer. Now, this is a natural number, so these are both positive, so k would have to be positive. But k is an integer, so if I multiply k by 1, or k times 2, or k times 3, notice that this number will always be bigger than or equal to x. So if I multiply a number by 1, I get the same thing. If I multiply by 2, I end up with a bigger number. If I multiply by 3, it's a bigger number. If I multiply by 4, it's a bigger number. So what that means is that if x divides a, then a is greater than or equal to x. Therefore, if I take all the elements in here, so if x is in C, then x, or 1, is less than or equal to x is less than or equal to a. And we know 1 is less than or equal to x because we're only looking at natural numbers. And we know x is less than or equal to a because x divides a. Therefore, do we have an upper bound on how many how many elements can be in C? Well, just going from this, the only options we have now are 1, 2, 3, 4, 5, 6, 7, all the way up to a. So the most elements we can have in here is a elements. Therefore, we could say the cardinality of C is less than or equal to a. So if the cardinality of C is less than or equal to a, and a is a finite number, that means that C is finite. So what I've shown is that all of the numbers in C have to be between 1 and a. So therefore, there are at most a elements in C. So therefore, C has to be finite. So what we end up with is C is a non-empty finite set. Therefore, it must have a greatest element, a unique greatest element, and that unique greatest element will be the greatest common divisor. So our greatest common divisor is well defined. That is, if I say the greatest common divisor of a and b, there is one and only one answer for that. Questions on that at all? So here, to show something exists and was unique, instead of trying to do that directly, I showed that, well, it's in a set, and this set is finite and non-empty, therefore it has to have a greatest element. So I get both the existence and uniqueness from my previous lemma, or previous theorem. All right. So the greatest common divisor exists. Now remember, I wanted to show it looked like something. It looked like the greatest common divisor looked like a times k plus b times l. So not only do I have to show it exists, but I also have to show it satisfies that property. So I'll look up. This was our original theorem. I wanted to show that it's equal to ak plus bl for some integers k and l. So, is a further detour away from our theorem. What I'm going to do now is I'm going to look at, well, instead of just showing that the greatest common divisor can be written at that, let's look at all of the things that can be written like that. So let's find all x such that x can be written as ak plus bl for k and l integers. Now, they're going to be infinitely many if I just allow k and l to go on forever. So I'm going to put an upper bound on it. So that is, I only want natural numbers. So I'm going to say 0 is less than x. But I'm going to say all the ones that are less than or equal to a. So just to put an upper bound on it. So by putting the upper bound, I'm going to make it a finite set. And now I need to show that it's going to be a non-empty set. So if I can show this is a finite non-empty set, then it must have a smallest element. So if I find all the things that look like this, well, all the things that look like that I'm saying are finite and non-empty, so it has to have a smallest element. And what I want to show eventually is that my greatest common divisor will be in this set. And if I can show my greatest common divisor is in this set, then I get my theorem. But first, I'm going to show that this has the smallest element. Well, it follows that it's finite by definition because I have at most A elements, exactly the same as we had before. And if you want to show it's non-empty, you just have to show something's in there. So something would be A, for example, because A is equal to A times 1 plus B times 0. So A is in the set, little a is in the set big A. So it is a non-empty finite set. So therefore, it must have a smallest element. So this lemma actually follows pretty quickly because we've defined it so it's finite. And we know it's non-empty because we can just pick A, which is why I put the upper bound at A, so that we had something in there. Now, what I'm going to say is, eventually I want to show that the greatest common divisor is indeed equal to the smallest element of that set. So, if I let A be as in the last lemma and D be the smallest element of A, what I want to show is that D is equal to the greatest common divisor of A and B. Now, just as a point so that we can keep track of where we're headed overall, is that if we can do that, that means that the greatest common divisor is indeed an A, so therefore it can be written as A times an integer plus B times an integer, which was the original theorem we're trying to show. So if I can show that the smallest element of that set is indeed equal to the greatest common divisor, then we have our theorem. Well, now what are we going to do is, in order to show that these two things are equal, we're actually going to show that D is less than or equal to the greatest common divisor, and that the greatest common divisor is less than or equal to D. Because remember, if A is less than or equal to B is less than or equal to A, they must be equal. So we're going to use that concept to get that these things must be equal. All right. First thing I'm going to do is show that the greatest common divisor of A and B is less than or equal to D, which is the smallest element of that set A. Well, what I'm going to do for that is notice that D was in the set, so D can be written as A times K plus B times L for integers K and L. All right. So this is where I'm headed. I know this because all the things in A can be written as this. Furthermore, 0 is less than D is less than or equal to A. But what I notice is that A, the greatest common divisor of A and B, actually divides A. So A is equal to the greatest common divisor of A and B times, let's say, K1 times K. And B is the greatest common divisor of A and B times, let's say, L1 times L. Because the greatest common divisor divides A, so therefore this times some integer is A, and this times some integer is B, so I'm just rewriting that. What does that mean is I can factor out the greatest common divisor, and I get the greatest common divisor of A and B is K1 times K plus L1 times L. Notice then that this is an integer, so what we have just proven is that the greatest common divisor of A and B times an integer is equal to D, so it divides D. But what we showed in the last one is we know both of these are positive. So if these are both positive and this divides this, that implies that the greatest common divisor of A and B is less than or equal to D. So by showing this divides this, we get this is less than or equal to this. So we do get that the greatest common divisor of A and B has to be less than or equal to D. Half done. Other direction. D is less than or equal to the greatest common divisor of A and B. Well, how are we going to do this one? Well, I don't know. Let's think about this. Well, why would I think that this would happen? I don't know. But what I want to say is, if I can show D divides A and D divides B, then D is a common divisor of A and B. Therefore, if D is a common divisor of A and B, it has to be smaller than the greatest common divisor of A and B. So if I can show D divides A and D divides B, I will get that D is less than or equal to the greatest common divisor of A and B. So that's where I'm going. So I want to show D divides A. So how am I going to do that? Is note that, well, I know that I can always take a number divided by another number using the division algorithm. I'll get A is some integer times D plus some integer R with 0 less than or equal to R less than D. And so we had talked about the division algorithm. We started talking about proofs, and we said it was going to be very helpful. And here it is again coming up. If I take A and I divide by D, I can get A is QD plus R for some R. Now, the goal is to show that D divides A. So that means that what we want to show is that R is indeed equal to 0. All right. Well, the way we're going to do this is by way of contradiction. Assume that R is not 0. Then we know that since R is not 0, 0 is less than R, is less than D, is less than or equal to A, because we already know that D was in the set where it was defined as being less than or equal to A. So everything in A is less than or equal to A. So 0 is less than R is less than A. All right. What in the world? How does that help us? Well, if we actually look at this, we get R is equal to A minus Q times D. But D was in that set A, so it can be written as A times some integer plus B times some integer. And so if I rewrite that, I get 1 minus Q times K times A plus B times, plus B times negative Q times L. And just to remind us, A was the set of all x such that x looked like AK plus BL, and 0 was less than x is less than or equal to A. Why in the world did I do that? Well, notice this is an integer, and this is an integer. So what I get is R is an integer times A plus an integer times B. So what does that mean? Well, since we assumed R was greater than 0 and less than or equal to A, that means that R is in A. Because it can be written in this form, and it's between 0 and A. However, there's my contradiction. It might be hidden. But the idea is that since R is in A and R is less than D, that contradicts the fact that D was the smallest element of A. So we define D as the smallest element of A. But if R is in A and R is less than D, that means D is not the smallest element. Therefore, we have a contradiction, so that means R can't be in A. So therefore, R has to be equal to 0. And since R is equal to 0, A is Q times D plus 0. So D divides A. Notice, I know there's a lot going on here. I hope you guys are kind of following along, but the idea was we showed that if R was non-zero, we could rewrite it as an integer times A plus an integer times B. Therefore, it had to be in this set, but that contradicted the fact that D was the smallest element of the set. So therefore, it can't be in this set, so therefore it has to be 0. Therefore, D has to divide A. If I go through this as well, I can also show that then the same argument shows that D also divides B. I'm not going to walk through the whole thing because it is just interchange A's with B's. But you get that, okay, so D divides A and D divides B. Therefore, D is a common divisor of A and B. So it must be less than or equal to the greatest common divisor of A and B. So we get out what we were looking for. But now we know that D is less than or equal to this, is less than or equal to D. Therefore, that implies that these are equal. Therefore, since D was in A, the greatest common divisor of A and B has to be in A. So therefore, the greatest common divisor of A and B can be written as A times an integer plus B times an integer. And that is our theorem. Like I said, there was kind of a lot going on there. You kind of lost track of where we were once in a while. But we're taking it step by step to say, okay, here are some interesting things we can do. We can use finite non-empty sets. We can use the division algorithm. We can use proof by contradiction, or a direct proof, or a constructive proof. Or we could do all types of different things to show existence and uniqueness. And we've kind of built in all of the different proof techniques we've had so far into one big proof. So that if you look back over this and you rewatch, you can take each of those individual parts and use those on your homework or use those on your test as illustrations of different ways you can do different proofs. So I hope that you take something away from that and you enjoyed that. I know I did. That is a fun proof. And like I said, I really like this theorem because I do end up using this a lot, even in future classes. So it is an extremely helpful theorem to know. All right. I don't see any more questions there, so I'm going to go ahead and move on. I have one more theorem I wanted to show today, and then I was just going to show that here I have a non-constructive proof. So that means I'm going to show existence, but I'm not actually going to construct or figure out exactly what those things are. So I'm going to show there exist two irrational numbers, x and y, such that x to the y is rational. All right. So how am I going to do that? So the point here is I want to take two irrational numbers and I want to raise one to the power of the other and show that I must get a rational number. And so what I'm going to do is the only irrational number that we've proven is irrational so far is the square root of 2. So let's just try the square root of 2 to the square root of 2. All right. So if we take the square root of 2 to the square root of 2, do I have any idea what that is? No, I really don't. There's no nice way to simplify this. So anyway, there you go. However, if this is rational, then I'm done, right? Because I have an irrational to an irrational is rational, so I'm done. Otherwise, let's assume that it is not rational. So let's assume that this is not in Q. So the square root of 2 to the square root of 2 is irrational. I actually don't know which one of those is true. So but it is either rational or it's irrational. If it's rational, then I have an irrational to an irrational is rational, and so I've proven my theorem. On the other hand, if this is not rational, then I can take the square root of 2 to the square root of 2 to the square root of 2. And notice that I then have an irrational to a rational. But what we get here is, because we have an exponent to an exponent, I can multiply. So I get the square root of 2 to the square root of 2 times the square root of 2, which is the square root of 2. Square root of 2 times the square root of 2 is 2. So the square root of 2 squared is 2. And since 2 is rational, we have an irrational to an irrational is rational. Now what I want to point out here is that this highlights that I don't actually know which one of these answers is an example. But I came up with two things where either this is an example or this is an example. So an example has to exist. I just don't know which one of the two it's going to be. So that would be a non-constructive proof saying, okay, I know it exists. I just don't know which one of those it's going to be. And I wanted to go through that namely because there is a homework problem like that as well. So I'll just give you an example for you guys to work with. All right. Any other questions from you guys? All right. With that said, then, I feel like we had a very constructive day. So I'm going to let you guys go there. On Thursday, I plan on going through some of the homework from this section. So if you guys want to look ahead, I can't remember off the top of my head what chapter it is, but I can post it on Blackboard. Look at those problems and see if you have questions so we can do them together on Thursday. And if we get done quickly, I might start something new. If not, if it takes a while to get through the homework problems, that's great too. Whatever, helps you guys. Heads up, because I brought it up in my last class, there is a test in this class next Thursday. It's going to be a take-home exam. So I'm not sure if I'll do a review on Tuesday or I might just do a review next Thursday and then give you the test after class, and then it'll be due the following Tuesday. That's probably the more likely scenario. So we'll probably have some lecture on Tuesday, and then on Thursday we'll do the review so that you're ready for the test after class. I will put the practice exam up by this Thursday so that you have a week to look it over and ask any questions along the way. Any other questions from you guys right away? A homework question on homework due tonight. Sure, which one? Or what is the homework question? All right, number 8 from chapter 10. All right. So number 8 on chapter 10, I'm going to write it up at the board, is suppose that a, b, c are integers and a squared plus b squared equals c squared, and I want to show that a is or b is even. So let me write that up here. I always like more practice, and we have some time, so that sounds good. So let a, b, and c be in z if a squared plus b squared equals c squared, then a or b is even. Now, at this point, I do want to put on chapter 10, this is the proof by contradiction chapter, but they told you that you could use direct proof, contrapositive, or contradiction. So you can use any technique you want. And so what I want to do here is I'm going to do some type of contrapositive or contradiction. And so the contradiction to an if-then would be assume. So negating an if-then, remember, was this is P and not Q. So assume that a squared plus b squared is equal to c squared, and a or b are even. And then I want to negate that. All right. So to point that out, if P then Q, if I want to negate that, this is not P or Q, which becomes not P is P and not Q. So I'm going to do a proof by contradiction. So the first step is to negate the statement. So I'm going to say P is a squared plus b squared is c squared, and not Q. So not a or b are even. So if I negate A or B are even is A is even, or 2 divides A, or 2 divides B. So now I want to negate that. So help me out here, guys. What is the negation of 2 divides A or 2 does not, or 2 divides B? Well, the or would become an and the divides would be not divides. So this would be and A is odd and B is odd. So the first thing I'm doing is trying to set this as a contradiction. To contradict an if-then statement, I rewrite it as assume P and not Q. So I get to assume A squared plus B squared and A is odd and B is odd, and I want to run into some type of contradiction. Does that make sense? Questions so far? All right, very good. All right, I'm going to need some more room. All right. So where are we going to get a contradiction here? Anyway, let's just think about this. I'm trying to think about, I know where the contradiction is going to be. I'm just trying to think about the best way to explain where to go from here. So what I would just do is start off with this side and just think about what does A squared plus B squared look like? Well, I know A is odd, so therefore what is A squared? A squared would also be odd, right? Therefore B squared is odd for the same reason. B is odd, therefore B squared is odd. So what happens if I take an odd plus an odd? I think an odd plus an odd is even, right? So what I would say here is that A squared plus B squared is congruent to 1 squared plus 1 squared mod 2 is congruent to 1 plus 1 mod 2 is congruent to 0 mod 2. Is that making sense so far? All right, so what does that mean? Well, that means that C squared is congruent to 0 mod 2, doesn't it? Because C squared is equal to A squared plus B squared, which means that C squared is even. But if 2 divides C squared, we know that 2 divides C or 2 divides C, so C is even. Does that make sense so far? All right, good. So now what I get is I get a squared plus b squared is congruent to c is even, so this would be 2 times k squared. So, or is equal to 2 times k squared, so a squared plus b squared is 4k squared. Therefore, a squared plus b squared is congruent to 0 mod 4. I am going somewhere with this, I promise. I'm just trying to take my time with it and make sure we really follow what's happening. Is the idea is c was even, therefore I can replace c with 2k. So therefore, what I get is a squared plus b squared would be even, but not only is it even, it's also divisible by 4. So now what I want to go back to is that I'm actually going to go back to the definition that an odd looks like 2k1 plus 1 squared and 2k2 plus 1 squared. And if I actually multiply this out, I get 4k1 squared plus 4k1 plus 1 plus 4k2 squared plus 4k2 plus 1 is equal to, and if I separate this out, I get 4k1 squared plus 4k1 plus 4k2 squared plus 4k2 plus 2. And there was some arithmetic in there, but I'm just foiling it out and I get this. Now here's the contradiction, and it's not easy to see this, but the idea is that if I take this mod 4, I get 0 plus 2 mod 4. So I get 2 mod 4. Well, what does that mean? Well, it means that because c was even, c squared was congruent to 0 mod 4, but it was also equal to a squared plus b squared. So what I get is 2 is congruent to a squared plus b squared mod 4 is equal to c squared mod 4 is congruent to 0 mod 4. So what is my contradiction? My contradiction is that 2 is not congruent to 0 mod 4. 2 is not equal to 0, therefore I have a contradiction. So if both a and b were odd, then a squared plus b squared would be even, therefore c squared would be even, therefore c would be even, which implies that an even number squared is divisible by 4, so a squared plus b squared is divisible by 4. However, if I square out two odd numbers and I divide by 4, I'm going to get a remainder of 2. Since 2 is not 0, therein lies our contradiction. I like that question. That's not obvious. I can see why you get stuck in there, is because you don't exactly know, where do I go with this? What do I do? So the point is I'm just trying different things. I'm just saying, okay, well, let's suppose they're both odd. What does that mean? Well, it means that add them together I get an even. What does that mean? Well, that means something else. But also it means that, well, if they're both odd, then what else has to happen? And so notice that eventually, and I wouldn't expect this to be right away, which is also one of the reasons why I say on the homework you don't necessarily need to get them complete. I just want you to think about them. Is that eventually, though, if you do keep working with this, you'll say, oh, well, on one hand I have 2, on the other hand I have 0. 2 is not 0, so therein lies my contradiction. Is that clear enough? If you guys do have more questions on the homework that's due tonight, we can also do that on Thursday. Do the best you can for tonight and turn in what you have, so that, and then if you want to talk about some of those on Thursday, we can, or we can talk about the homework that's coming up for next Tuesday, and I'll spend time answering whatever questions you guys may have. All right. Well, anyway, I'm going to leave it there. Thank you guys very much for joining, and I hope you have a wonderful day, and I will see you on Thursday. Welcome.